this is the third lecture on proofs in Indian mathematics. So, we shall concentrate on in the large part of this lecture on the proofs of the results that sort of pertain to calculus, the discoveries of Madhava. So, where really one has to take this limit of some quantities for large n. So, how does Yukti Bhasha handle these kinds of proofs is what we will be discussing in this lecture, and in the end we will have some general comments about Upapatti and proof and some comments on history of mathematics. So, as we have repeatedly said, the most detailed exposition of proofs or Upapattis in Indian mathematics is found in the Malayalam text Yukti Bhasha of Jeshtadeva. Yukti Bhasha sets out or states that its purpose is to give the rationale of the results and procedures presented in Nilakantha's Tantra Sangraha. This book is in Malayalam. So, many of these rationales have also been presented mostly in the form of Sanskrit verses by Shankar Warrior, a pupil of Nilakantha, in two commentaries, Kriya Kramakari on Lilavati and Yukti Deepika on Tantra Sangraha. Yukti Bhasha has 15 chapters. It is chapter 6 which deals with the Madhava series for pi, it is the chapter on the Paridhi Vyasa Sambandha. Chapter 7 is the chapter on Jnanayana, which deals with the Madhava series for the or sign and or word sign. So, let us straight away look at how Yukti Bhasha tries to estimate this sum. This is called Samaghata Sankalita. Sankalita is the sum, Ghata is a product, Samaghata means equal powers. So, sum of natural integers of the same powers. We have to find out how this sum behaves for large n. We have to have an asymptotic estimate of this sum, and this is at the heart of development of calculus. Estimating this was a major effort in whole of 17th century efforts in Europe, which arrived ultimately at the development of calculus. Yukti Bhasha has a statement of the result and a proof of it. So, we shall discuss the proof. First, it is noted that the sum of the first powers, we have Aryabhata's exact result n into n plus 1 by 2, and obviously for large n you can neglect the n by 2 term and you can say this goes like n squared by 2. So, it is this careful separation of the orders in which as n becomes large, what is the significant term, or in 1 by n as n becomes large, what are the terms that can be neglected. This is where the heart of this limiting operation comes. Now, for Sn2, this is the Varga Sankalita. Of course, we know the exact formula is available. So, we can again look at it and write down the asymptotic behavior for large n, but Yukti Bhasha chooses to start writing down the proof in the way it will do for the general case, so that you understand the method of proof in the general case. So, it says write this Sn2 in this way, n squared plus n minus 1 squared etc. plus 1 squared. Subtract from Sn of 2 n times Sn of 1, n times the Moola Sankalita 1 plus 2 plus etc. n, and when you subtract, n Sn1 minus Sn2 becomes 1 into n minus 1 plus 2 into n minus 2 plus 3 into n minus 3 plus etc. plus n minus 1 into 1. Now, remember Yukti Bhasha does not have any symbols, any diagrams, all these are set out in terms of sentences, all these equations are explained in terms of sentences, all diagrams are explained in terms of sentences, but to write diagrams they will tell you start from the east corner, go to the northwest corner, then look at the place where this line cuts the circle. So, they have a very nice way of describing the geometrical diagrams. In the same way, these algebraic results are stated in verbal form. So, n times Sn minus 1 minus Sn2 therefore can be written as n minus 1, then these 2 n minus 2's can be written this way, the 3 n minus 3's can be written that way, the n minus 1's can also. So, now you resum them, that is now you look at this sum this way, you look at the sum this way. So this is Mula Sankalita up to n minus 1, this is Mula Sankalita up to n minus 2, etc. So what we have, so n Sn minus 1 minus Sn of 2 is Sn minus 1 1, Sn minus 2 1, Sn minus 3 1, that is Mula Sankalita going up to n minus 1, Mula Sankalita going up to n minus 2. So this is the, if it is not clear we can look at it once again, Sn2 minus n Sn1, we write like this and then rewrite it and sum it horizontally now, and therefore we have this identity. So this is at the basis of the Yukti Bhasha proof actually. They will later on generalize this identity and prove the result by induction. So since we have already estimated the Mula Sankalita summations of the first powers of natural integers to go like n squared by 2, so we substitute here. So Sn minus 1 we write it as n minus 1 whole squared by 2, Sn minus 2 1 is written as this, Sn minus 3 is approximated by this, and so on. And now you again behold that this is sum of the squares of integers. Of course for large n the later terms are not of significance, and so this whole sum can be written as the square of the first n minus 1 integers, the sum of the squares of first n minus 1 integers divided by 2. So you have an equation like this. Now this Sn minus 1 of 2 and Sn of 2 are almost the same. When n is very large, there is no difference between the sum of the squares of the first n integers and the sum of the squares of the first n minus 1 integers, at least for the purpose of the large n behavior which we are estimating now. So these two can be taken to be the same. Therefore taking this to the right hand side, this will become Sn of 2 1 by third of that, 3 by 2 of it, and here already NSN1 is there. Therefore finally you will get Sn of 2 goes like n cube minus 3. In case this step is not clear, what we have shown is n Sn of 1 minus Sn of 2 goes like Sn minus 1 of 2 by 2 right. This is what we have shown. Now you take this to the right hand side, so you just get Nsn of 1 approximately equal to Sn of 2 3 times, right. These two are the same and this has already been estimated. So Sn of 2 goes like 2n by 3 Sn of 1. What is Sn of 1? It goes like n squared by 2, we have already estimated that for large n. Therefore we have Sn of 2 goes like n cube by 3. All this is set out verbally in Yukti Bhasha or in Kriya Kramakari commentary on Lilavati. Similarly, it is shown that the sum of the third powers of integers goes like n to the power 4 by 3 for large n. This argument is also explained in detail in Yukti Bhasha, same kind of argument. Now follows the argument by mathematical using mathematical induction to demonstrate the same estimate for a general Samaghata Sankalita. So he is saying, suppose you are interested in summing the Samaghatas where it goes up to some gacha, some number. For that you take first n times the Samaghata Sankalita of the lower order and subtract the Samaghata Sankalita of the given order. So same thing that we did for Nsn1 minus Sn2. Then this argument is given by recombining these terms, that this is actually equal to the repeated summation of Sn minus 1 of k minus 1, the Vara Sankalita of the lower order Samaghata Sankalita. That is how it is explained. So this relation is just like this relation, only this is k minus 1 and this is k. The argument is very similar to prove this. So this is the basic relation, and this relation there is no estimate involved, it is exact. Now we argue what happens when n becomes large. So in all of Yukti Bhasha, up to a point the terms of all n are kept and its exact results are written, and then the final limit and arguments are made. So this result is exact, that Nsn k minus 1 minus Sn of k is this. Now if we have already estimated, that is how a mathematical induction argument works. First you write down a relation then assume something for n and then show it for the n plus 1, and then you have shown it for all n if you have already shown it for n is equal to 1. So assume that the k minus 1th order Samaghata Sankalita has already been estimated and it goes like n to the power k by k. Once you assume that and put that into this equation, so this has already been estimated, so each of these go like n minus 1 to the power k by k minus 1, n minus 2 to the power k by k, each of them goes like this, n minus 1 to the power k by k, n minus 2 to the power k by k, n minus 3 to the power k by k. So this is looking, of course, terms which are very small in the other end do not matter, and this is clearly looking like the sum of the kth power of integers from 1 to n minus 1. So it is nothing but Sn minus 1 of k by 1 by k for large n. So the previous one was an exact relation, from that for large n we have this. Of course there is some argument about finally this is going like 1 to the power k by k kind of term is also coming there. So is it really true, is it really correct? So a more technical argument needs to be made, there is a small sort of epsilon delta argument that needs to be made to justify this. This justification for instance has been indicated in the papers of C.T. Rajagopal, who says one can use the same sort of arguments used in the proof of something called the Cauchy-Stolz theorem to justify this step very rigorously. So once this has come, the argument is just the same. Sn minus 1 of k is almost the same as Sn of k. So if you use the already known estimate of Sn of k minus 1 for this, you will obtain Sn of k is n to the power k plus 1 by k plus. This is one of the beautiful proofs in Yukti Bhasha for the Samaghata Sankalita for large n. Now the estimate of Vara Sankalita. So for Vara Sankalita, what is Vara Sankalita? Repeated summations, not summation of powers, but summations repeated. So first summation is 1 to n, that is n into n minus 1 by 2. Second summation is sum of these n into n plus 1 by 2, you sum it from n is equal to 1 to n is equal to m. How will it look? So in general the rth order repeated summation is the summation of the r minus 1th order from 1 to n. That is the definition of the Vara Sankalita, and as has been said repeatedly, this was clearly the result for this was enunciated in Ganita Kaumudi of Narayana Pandita, that the rth order summation is this. And so how does it behave for large n? How does it behave for large n? It goes like n to the power r by r, n to the power r plus 1 by r plus 1 factorial. There is one n factor in each of this. So the highest power of n that occurs in the numerator is n to the power r plus 1. So the way Vn of r goes for large n is n to the power r plus 1 by r plus 1 factorial. So once we have Narayana's formula, you have this n into n plus 1 etc. into n plus r by r plus 1 factorial. So immediately you can see that it goes like n to the power r plus 1 by r plus 1 factorial for large n, right. In each of them there is an n term, and so the largest power that will occur in the numerator is n to the power r plus 1. The next term is of the order n to the power r, which can be neglected in comparison to n to the power r plus 1, n goes to infinity. But Yukti Bhasha knows this result, the authors of the Jeshtadeva knows this result, but he does not want to use this to write down the proof. He wants to write down an argument by mathematical induction in the same way as he did for the summation of powers of n. So an argument like this he wants to do. So that is the thing that we will give now. So the first order summation we already know, that result given by Aryabhatta n into n plus 1 by 2, it goes like n squared by 2. Now say, let us write Vn of 2. We already know the asymptotic behavior of Vn of 1, that goes like n squared by 2. So the same thing for n minus 1 and go on down the line. Therefore asymptotically for large n, Vn of 2 behaves in the same way as Sn of 2 by 2. There we already know Sn of 2 goes like n squared by 3. So Vn of 2 will go like n cube by 6. So restating it in the general case, Yukti Bhasha says Vn of r goes like is equal to Vn r minus 1, Vn minus 1 r minus 1. The r minus 1 sum we have already estimated goes like n to the power r by r factorial. So each of these terms can be replaced by n to the power r by r factorial, n minus 1 to the power r by r factorial, etc. Again the lower order terms do not matter for large n. So this is nothing like the sum but the sum of the rth power of integers, that is Sn of r divided by r factorial. Sn of r is n to the power r plus 1 over r plus 1, therefore Vn of r goes like n to the power r plus 1 by r plus 1 factorial. So this same induction argument, assuming the Samagata Sankalita, they are writing it for the Vara Sankalita. It is in fact even more interesting, one could go from this to this. One could have used this to prove Sn of k goes like n to the power k plus 1 by k. In fact that is the route Pascal or Fermat took in 17th century. They conjectured this result, Pascal actually proved this result, Fermat I think conjectured this result, and from this one could get the asymptotic form, and from that one could get the way the Samagata Sankalita. So it is either way. And as I told you, this result was already implicit in the Varaha Mihira's table Meru for calculating the combinatorial coefficients in the 6th century. The sum of integers, sum of integers, sum of integers is the number of combinations, and that is a NCR kind of term like this. Okay. So this is about one of the most important results in mathematics for development of calculus, which is the estimate of this. You see the first order sum and second order sum were known to Aryabhatta, they were known to the Greeks also, and in some of his what is called the quadratures of parabola, etc., Archimedes used the asymptotic behavior of the sum of squares. Of course he worked out an argument in the standard Greek way by reductio ad absurdum for that. The fourth powers were summed by I think Ibn al-Haytham in 11th century in West Asia. So he had an estimate for the fourth powers, but the Samagata Sankalita of the general order, a result like this was first given by Yukti Bhasha along with a proof also. They had of course this estimate for the Vara Sankalita also. Both are used in the subsequent result that we are now going to discuss. So now the derivation of the Madhava series for pi. So what is done? There is a first part is a purely geometrical argument, converting the length of an arc into an algebraic expression through the use of geometry. And as you can see how sophisticatedly Indians were arguing with the geometrical magnitude, you can see here how they converted it into an algebraic expression, and then a limit of that algebraic expression is taken for large n, which is where calculus comes in. So what is the derivation of Madhava's series? So you take this quadrant of circle, the circle is of radius r, draw this square that circumscribes the circle. Now for this quadrant, this portion, this side of the square EA is the same as the radius of the square. So you have a square of radius r. Now divide this radius into n equal parts. We are not dividing the arc into n equal parts, we are dividing what we today call as the tangent into, that is the beauty of this Madhava's derivation, that makes gives you a nice formula that you can handle for the length of this curve. So divide this tangent into n equal parts and join these hypotenuse at, so this may be the nth bit of this. So EA is divided into n equal parts, EA is of length r, so each of these bits are of length r by n. Join this OA1, see where they meet the circle, draw a perpendicular from there to the, so these karnas, from these 2 points in one karna, draw perpendiculars to the next karna. So this is the geometrical construction. What is the next thing? Of course it is noted that the whole calculation will have to be done for when n becomes very large and the bits becomes very sukshma. So first thing is two similar triangles, AI PI AI plus 1 is similar to OE AI plus 1, this is one. So to argue this similar triangle, it is argued that the sides of one triangle are perpendicular to the sides of the other triangle, and the example of the Kerala temple, those intersecting those wooden sort of beams is what is mentioned in Yukti Bhasha. It is like those wooden beams where one sides of one triangle are perpendicular to the side. So it is said that Madhava got this proof by sitting inside a Kerala temple and contemplating. Then another thing is OCQJ, this triangle is same as OAIPI, both of them arise by drawing perpendiculars from one line to the other line, so they are similar. So this argument from similar triangles immediately gives you an expression for the sign of this arc bit. Ci plus 1 is an arc bit that is wedged between these two Karnas, where it is the ai plus 1 which are equal. So the Ci plus 1 are not equal, but they are small. So the argument now is this Ci plus 1 when n is very large can be approximated by Ciqi, the sign of the same arc bit, and therefore this 1/8 of the circumference, that is the circumference from E to C, because this is the last Karana, this radius is divided into n equal parts. You are estimating the Ci plus 1, and each of them is written in terms of this OAI plus 1 and OAI plus 1 and OAI, they are called Ki plus 1. So immediately get this nice expression for the. So you have converted the arc of a circle into a beautiful, in the limit of course of large n, an algebraic expression. Now you are going to play with this only. Geometry is over. C by 8 goes like r by n into r squared by k naught kn, r squared by k1 k2, r squared by kn minus 1 kn. Ki's are these Karnas OAI plus 1. So next is when n is very large, these Ki's are very close by, this is argued out also, and so the earlier sum, this sum is replaced by this sum, and actually their difference is actually shown to be negligible when n is fairly large. And now the next step is to realize from geometry that each of these Karnas is actually Eai squared plus Eo squared, and Eai is obtained by the after the I arc bits are over. Therefore Eai is I times r by n, OE is of course r itself, and therefore Ki squared is r squared plus IR by n squared, and you have obtained this expression. So except for the left hand side where you are saying this is approximately equal to C by 8, all this is there on the right hand side has been more or less exactly manipulated, no approximations are made except for this one which is justified. Now if anyone who has done his calculus and has written an integral as a sum, as a set of sums, can straight away realize that you remove the r squared as a common factor out, this is nothing but integral of 1 over 1 plus x squared dx from 0 to pi by 4, that is the integral of the tan inverse x function, which will give you pi by 4 as the answer. So now what is the next step? Next step are two which have already been done. One is this denominator is expanded using binomial series, which you have already done. So using binomial series expand each of these denominators, so that is the first step, and group together terms involving same powers of n. So you will have a term involving sums of integers, you have a number involving squares of sums of integers, you have a term involving sums of integers taken to the 4th power. So use the second thing that we have done, the estimate of the kth power of the Samaghata Sankalita when n is very large, and therefore you will immediately obtain when n is large, this is take out the r take out the r, so you have 1 to the power 4, 2 to the power 4 etc, n to the power 4, that goes like n to the power 5 by 5, this will go like n cube by 3, and this will go like n squared by, this go like n. So that will cancel with that n, and this will cancel with the n into n squared n cubed here. So you have finally the series of Madhava C by 4d 1 minus 1/3 plus 1/5 etc minus 1 to the power n 1 over 2n plus 1. Next is the derivation of the end correction terms. So the Madhava series is written this way, and as we have remarked, it is a very slowly convergent series. So let us assume an end correction term like this. Now Yukti Bhasha and Kriya Kramakari, Madhava has actually given these end correction terms. Yukti Bhasha and Kriya Kramakari will tell you how to derive them. So for the derivation, all that you have to say is, let us assume that 1 by AP gives the exact value. Let the end correction be such that, then suppose I terminate the term at series at P minus 2, then 1 by A P minus 2 should also give me the exact value. So you have to equate the exact values with 1 by AP here and with 1 by AP minus 2, immediately you get an equation like this. So this equation is at the heart of the estimation of AP. We use this to estimate AP. Now looking at it, one can say trivially take 1 by AP as 1 over 2P and everything is done. That is not correct, because if you take AP as 2P, then AP minus 2 will have to have same dependence on P minus 2 as AP has on P. So AP minus 2 will have to become 2 into P minus 2. Similarly, if you take AP minus 2 as 2P, then AP will have to be equal to 2 into P plus 2. So there is no simple integral and that kind of solution. You have to have a fairly complex expression involving P. So it is a functional equation in P which will be sort of complex, which has a fairly complex behavior. But what we do is, this quantity EP is equal to 1 by AP plus 2 plus 1 by AP minus 1 by P is called the inaccuracy Staulya by Yukti Bhasha. We will successively approximate this Staulya and obtain end correction terms. So the first approximation to the end correction is AP is equal to 2P plus 2. If we put this, if this Staulya is equal to 0, the result is exact. I mean that end correction divisor is giving you the exact value of the Madhava series, but Staulya can never be 0. So if you put AP is equal to 2P plus 2, you just a algebraic. So this algebraic manipulation is very beautifully explained in Kriya Kramakari, putting various boxes and all that. So how to keep the different polynomial coefficients in hand. You are going to have ratios of polynomials in P in general whenever you do this kind of manipulation. So you get 1 by PQ minus P. So supposing I had chosen instead of 2P plus 2, 2P plus 3, or I had chosen even 2P minus 1, this Staulya would pick up a P term in the numerator also. What is the disadvantage? As P becomes very large, this goes to 0 much faster than the other one. So this is a better term for the inaccuracy to have, that when for fairly large P you have a reasonably accurate result, whereas if you had chosen AP is equal to 2P plus 3, it will only go by like 1 over P squared instead of like 1 by P cubed. And you can already see that in this the Madhava transformed series is also coming. After all, this expression for Staulya is what Madhava manipulated in this equation itself too, and that procedure was called Staulya Parihara. So use the error corrections in the series itself to transform the series. So you are obtaining a P cube minus P term by a correct choice of AP to first order. So this is the first order correction. Now of course our result is not exact, we still have EP which is non-zero. So to make it better, we have to add a quantity which depends on P but which is less than 1. So let us take A over 2P plus 2 as a next order correction to the correction divisor. Now if we choose A as equal to 4, we will immediately get Madhava's first correction divisor. The first correction that Madhava gave, you can recognize, is this. So for that A will have to be 4. Again the argument is, let us calculate EP with this AP. What is EP? EP is this 1 by AP minus 2 plus 1 by AP minus P. This is our EP. So let us calculate that with this expression for AP. Then we get EP is equal to minus 4 by P to the power 5 plus 4P if I take this. But if I take instead of this any other value for A, 3 or 5, then we will find that EP will pick up a P term in the numerator. So the Staulya will not go like 1 by P to the power 5, it will go much more slowly like 1 by P to the power 4. So we will not have a more fast decreasing Sthaulya. Therefore, for better this thing inaccuracy, we need to choose this constant to be 4. Next. So a final, and now by now the procedure is very familiar. They are also thinking of a continued fraction. We are also wanting a continued fraction. So we are going to get that. So 2p plus 2 plus 4 over 2p plus 2. Now you say let me take 16 over 2p plus 2, then the Sthaulya will go like this. Instead of 16, if I choose 15 or 17, this EP will pick up actually a p squared term now, not even a p term, it will pick up a p squared term in the numerator. And in all this you can discover the Madhava transformed series is also coming here. Here also the terms like of the Madhava. So this derivation of the end correction term, this very brilliant one done in Yukti Bhasha. Many people had misunderstood it, that even till 1990s people were writing, when Yukti Bhasha was not analyzed, papers saying Madhava guessed the value of pi as 355 by 133 or 113 or something like that, and using it he tried to estimate the end correction term after knowing say 15 terms in the series or 20 terms in the series. This a very general and an argument that we would be proud to be doing in any course on real analysis today in our colleges. So the general correction divisor of Madhava is of the form 1 over AP 1 over 2p plus 2 2 squared. Of course this is not stated in Yukti Bhasha. This was first stated in a paper by Rajagopal and Rangachari as a continued fraction, and in fact this was pointed out by the great British historian of mathematics Whiteside, who has edited Thomas Newton's papers in 18 volumes. Now we go to Yukti Bhasha's derivation of the Madhava sine series. So again this is a day of sine today, it keeps coming in every lecture. So again the arc bit is somewhere here. Let us say we want to calculate the sine of this arc e to c, which is not marked in this diagram. Again divide that arc bit into n equal parts. Now we are dividing the arc into n equal parts, and Cj plus 1 is the jth arc bit in that. So S is divided into n equal parts, this is the jth arc bit. So at the jth arc bit the r sine is this, the r cosine is this, r versine is that. Cj Pj is the bhuja, that is Bj, r sine jx by n. Opj is the koti, which is Kj, r cos jx plus 1. Pje is the shara Sj, which is r versine jx plus e. Now that bit of derivation which we did not do, we are again going into the famous Aryabhatta second order sign difference formula. So that is dependent upon the similarity of these triangles Cj plus 1 Fcj, Cj plus 1 Fcj, and Mj plus 1 Gmj, Mj plus 1 Gmj. Mj plus 1 or Mj are the midpoints of the arc bits Cj, Cj plus 1 and Cj minus 1 Cj. Similarly OQj plus 1 Mj plus 1, that is O Qj plus 1 Mj plus 1, and OPJ Cj, OPJ Cj, they are straight away the sides are parallel. So those are similar triangles. So using these similar triangles, and we will denote the chord associated with the arc bit Cj, Cj plus 1 as alpha. Alpha is the chord associated with the arc Cj, Cj plus 1, alpha is the chord. So if we do that, we obtain Bj plus 1 minus Bj as alpha by r Kj plus half, Kj minus half minus Kj plus half, which is same as the Shara difference Sj plus half minus Sj minus half as alpha by r Bj. So they are just using simple similar triangles in the example that we considered. So subtracting Bj minus Bj minus 1 minus Bj plus 1 minus Bj is a difference of Sharas, and it is equal to alpha by r squared into Bj. This is the famous Aryabhatta formula. Only this alpha by r squared is then to be written as delta 1 minus delta 2, the first sign difference. Now we just sum over these sign differences, and then we will get Bn minus n times B1 by an expression like this, and already you can see a repeated summation coming in here, B1, B1 plus 2, B1 plus B2 plus etc. Bn minus 1, and some of the Sharas, the difference between the last Shara and the first Shara is of this form. So these are the exact results, and now we start taking the limit when n becomes very large, we start making various approximations, and based on that we will obtain the expression for the R sine series. So when n is very large, Bn is approximately equal to B. Bn is the R sine associated with the nth bit, anyway that will be equal to B even, there is nothing further to say. Yes, n minus half, the midpoint of the last arc bit, can be approximated by the Shara. Yes half, this is 1 minus cos theta, when theta goes to 0, this goes to 0. The chord associated with the arc bit, when n becomes very large, the chord and the arc bit can be equated to each other. So these two equations are therefore replaced by these two equations. The Shara associated with our arc, yes, the first approximation is this. The bhuja associated, the sign associated with our arc is. Now what is done is, each of these bhuja khandas, B1, B2, B3 etc., successive approximations are made for them, that is put into both these equations, and from that a new value for bhuja is calculated. From that new value for bhuja, the bhuja khandas are calculated again, they are flowed back into the equation, and then again new values for bhuja are calculated. We will see that in a second. So to lowest order Bj, we are going to take it to be equal to the arc itself. This is of course a very gross approximation. The Bj is, as you can see, this Pj Cj, this we are saying is equal to arc E Cj, is a very gross approximation. So to the first order we take Bj to be the arc itself. So the ja chapa difference, the difference between the ja and the chapa, here is taken as 0 to lowest order. Now you put this in, Bj goes from j goes from 1 to n. So we put this in these two equations, we get summation of numbers and summation of numbers, and our Vara Sankalita and the Sankalita estimates will come in handy. We put those, so 1 plus 2 plus etc. n minus 1, that goes like n squared by 2, 1 plus 2 into 1 plus 2 etc. n minus 1, that also goes like n cube by 6. So we put those two, we get Shara goes like s squared by 2r, bhuja goes like s minus s cube by 6r squared. You are already seeing the pattern, you have generated the first term in the sine series and the versine series. Now what do we do? For each of the Bj's we substitute from this equation. So we take the bhuja not to be equal to s, the first approximation was B is equal to s, second approximation for Bj is we take from this equation. So Bj is Js by n minus Js by n whole cubed by 6r squared. So we plow that into these two equations for Bj, and again summation of integers, summation of squares and cubes of integers will come, and you will get the next approximation for Shara, the next approximation for bhuja, s minus s cube by 3 factorial plus s to the power 5 by 5 factorial, and Shara is equal to s squared by 2 factorial minus s4 by 4 factorial. So again we plow this back, and by now we know the pattern, and therefore we can conclude that by repetition we will get the Madhava series for the sine and the Madhava series for the versine. So the series for cosine is 1 minus x squared by 2 factorial plus x to the power 4 by 4 factorial. So this was Madhava's proof of the sine series, or this is the Yuktibhasha proof of the sine series of Madhava. So apart from this, the only other proof in Yuktibhasha which involves using this large n limits is the proof of the surface area of the sphere and the volume of the sphere, which I think the volume of the sphere was covered in the earlier lecture on proofs. So these are the proofs that are contained in Yuktibhasha, which involve dividing an arc or a line into a large number of segments and working out a complex expression for the geometrical quantity that you want as an algebraic expression, and then playing around with it, and only in the end, after sufficiently far away in the game, you start taking the limit when n becomes very large, and use the asymptotic forms that have also been derived in Yuktibhasha and obtain the results, and it is a very sophisticated way of doing things, as we know. So we have more or less come to the end of the discussion of the various kinds of proofs that are found in Indian mathematical literature, starting from the simple proofs of the Pythagoras theorem to the fairly complex and sophisticated proofs of the infinite series for pi and the sine series of Madhava. So let us just summarize again. I had put these points in my inaugural or the introductory overview lecture also. At that time it might not have been clear what we were talking about, so we can go through these points somewhat more carefully now. So first point is that I am trying to compare the idea of Upapatti as found in Indian mathematics with the idea of proof that we commonly know, or which goes back to the Greek tradition or the modern European tradition of doing mathematics. So first is that it is clear that Indian texts say that even results of mathematics, which even those enunciated in authoritative texts, need some yukti or upapatti, and it is not enough that one has merely observed the validity of the result in a large number of instances, and great effort is taken to present these upapattis by these various commentaries that are written on text. These upapattis are presented in a sequence, and you go from known results to unknown results and things like that, and arrive at the result to be established. Now the purpose of the upapatti, they repeatedly emphasize, is to make you clear what the result that you are discussing or the process that you are considering, remove doubts about them, and to sort of make you understand how that in the community of mathematicians, make them appreciate and accept the result that you are proposing. Crucially, upapatti may involve observation or experimentation. It also may depend upon the prevailing understanding of the nature of the mathematical objects involved. So it is not a purely a formal or an abstract or a non-empirical exercise. So in that sense, mathematics was not thought of as a non-empirical science in India. Mathematical results did not have any other extra level of validity than results in other disciplines, where the results did depend upon observational validity of the result that was being enunciated. Only that you have some more logical argumentation to support your result is all that is perhaps extra. More crucially, that is of course not a fairly important point in itself, but more crucially this proof by contradiction is used only occasionally, and there are no upapattis, at least that we know of in Indian mathematics, which purport to establish existence of any mathematical object merely on the basis that non-existence of that object would contradict whatever else that we know, but we have no way of establishing its existence by any other direct means of validation. So this is called the, to some extent this approach is called the constructivist approach to doing mathematics. So there is no claim in Indian mathematics that the upapattis prove the irrefutably they prove the absolute truth of the given proposition, and there is no attempt made to write down a set of axioms once and for all and then obtain all results. The writing down axioms once and for all is important in a mathematical system which depends on the reductio ad absurdum. So because there the axioms are all put together, and anything that contradicts that is always used to prove other results further and further. In a tradition where reductio ad absurdum is not used in that way, more and more postulates keep coming on the way as you keep building up your mathematical framework. Axioms are not listed right at the beginning. And the last thing is that though several symbolic and formal sort of approaches to discussing and formulating mathematical problems were evident starting from Panini in India, there was no idea that mathematics dealt with non-empirical quantities, and there was no idea of formalization of mathematics. So in this sense, Indian mathematics is not bereft of a methodology, but seems to be an instance of an approach involving a fairly different and a sophisticated methodology that is different from what we have been acquainted with, because we are mostly acquainted with either the Greek approach to mathematics or the way mathematics has been developed in the last couple of centuries in Europe, where Europe also went back to the Greek approach. Now here is something that we see about did really all of history of mathematics, did it follow the Greek canon or the Greek method? The Greek method of mathematics starts with the text of Euclid, at least that is the first available text, which was written around 300 BC, called the Elements, and it almost ends, I mean Archimedes is the high point, and it almost ends with Apollonius around 1st century BC, and it is in astronomy it continues with up to Ptolemy in the 1st century AD. So it is about 350 years that mathematics is done this way. After that, though very high praise is given to the Euclid and the methodology of mathematics that ought to be followed if we were following the Euclidean approach, most of development of mathematics occurs in spite of or independent of the Euclidean approach, and that is what I think which we should really be very aware of, because mathematics is almost presented as if they were going from proofs to proofs, all these from the time of Euclid to today. That is not the way it goes. So here is a statement from a very famous historian of calculus. This is a book written about 30 years ago. So he is telling us what is the lesson that we can understand from the history of calculus in the European tradition. However, vagaries of the external world were not by themselves responsible for the failure of Greek mathematics to advance materially beyond Archimedes. There were also internal factors, that because it said that the Greek mathematics died because of the persecution of the Greek mathematicians. There were also internal factors that suffice to explain this failure. These impeding factors centered on the rigid separation in Greek mathematics between geometry and arithmetic or algebra, and a one-sided emphasis on the former. Their analysis dealt solely with geometrical magnitudes, lengths, areas and volumes rather than numerical ones, and their manipulation of these magnitudes was exclusively verbal or rhetorical rather than analytic or algebraic, as we would say. This is more modern, but they would not think of the fourth power of a quantity because that cannot have a geometric representation. Indians did specialize in geometry, but they also applied algebra in a way. From the time of Katyayana Shulba Sutra, we are talking of n a square, which is n times another square. Now the more important point, it is somewhat paradoxical that this principal shortcoming of Greek mathematics stemmed directly from its principal virtue, the insistence on absolute logical rigor. The Greeks imposed on themselves standards of exact thought that prevented them from using and working with concepts that they could not completely and precisely formulate. For this reason, they rejected irrationals as numbers, excluded all traces of the infinite and even zero, such as explicit and things like explicit limit concepts from their mathematics. Although the Greek bequest of deductive rigor is the distinguishing feature of modern mathematics, it is arguable that had all the succeeding generations also refused to use real numbers and limits until they fully understood them, the calculus might never have been developed, and mathematics might now be a dead and forgotten science. This is a very serious book on history of calculus. This is not a philosopher. This is not like George Berkeley objecting to Newton's use of infinitesimal. This is a more sophisticated understanding of, because all of the calculus that we know and we teach is the reformulation that has occurred in the last 100-150 years, say ever since the notion of real number as was reformulated by Dedekind, or the notion of limit as it was reformulated by Cauchy in 19th century, and much more so after the elements of Bourbaki gotten written, which is the elements of the 20th century, which reflects the elements of the 3rd century BC of Euclid, reformulating most of mathematics inside a rigid, beautiful axiomatic framework. I am quoting David Mumford again to show the same point, not emphasized now by a historian. Edwards was a historian. David Mumford is a very eminent practitioner of mathematics, but who is aware of the Indian tradition somewhat deeply. He is a Fields medalist, as Professor Shira mentioned in some other context, but he wrote a review of this recent book on history of Indian mathematics, and then again the main point that he is trying to tell you is that Indians discovered several beautiful nice results, and what it does convey is that indeed all mathematics need not be done in the Greek way. Very beautiful and creative mathematics could be possible outside of the Greek framework, and it has indeed been so in history, and it often happens in the history of mathematics that beautiful mathematics does get done independent of the kind of rigor and standards that the Greeks have imposed on it from their times till today. So, these are all statements which are sort of profound philosophical significance, but that is not very important. In an ordinary sense, the fact that there has been an Indian tradition of mathematics where things were logically rigorously derived, but they did not do so in the manner that we are all aware of in the way Euclid's geometry is written, should show that there are indeed different ways of formulating, teaching, doing mathematics and even expanding mathematical knowledge in a valid way. There is another dimension to it, that this alternative approach to mathematics could indeed have been very fruitful even for contemporary times, only somehow that got cut 2-3 centuries ago. You see, ever since the work of Needham, it has been recognized that from till around 1600 the Chinese science and technology was much more advanced, especially the technology and also the science, than what prevailed in Europe there. But Needham, after having documented it, ended up with the question that why modern science did not emerge in non-Western societies. Now, in the work of Kerala school, at least we have discussed the mathematics part of it. It tells you some of the fundamental things that were rediscovered in most of 16th, 17th and perhaps even 18th century Europe, and some of them which were not discovered, like the alternative Chakravala algorithm or things like that. So, and similarly in astronomy, many things that were called hallmarks of emergence of modern science, like a alternative model of the planetary motion, etc. All these were there in Kerala school of mathematics. So, one should really in fact wonder first why non-Western societies did not continue with their ways of doing science, say after 16th or 17th or 18th century. That is more a historical question. It is not a question which is entirely internal to the history of these sciences. It is not merely because that these disciplines lacked certain methodological rigor or certain philosophical sophistication that modern science brought in, but much more so in a world that is now really becoming mix of various diverse civilizations. It is even more important that we should speculate what would have been the future trajectory of science if other civilizations continue to contribute significantly to science, or we can sort of speculate what will be the future of science if different civilizations now start contributing, as it seems to be happening, in a significant way, and then only we will be able to appreciate some of the creative geniuses in the modern Indian times, such as Srinivas Ramanujan or Jagdish Chandra Bose or Prafulla Chandra Ray or Raman, many others. Now, saying it may be sounding somewhat outlandish, but I am just quoting now a very professional historian of science whose name you have already heard half a dozen times, Takao Hayashi, who is a scholar of history of Indian mathematics. He is also a scholar of history of Korean and Japanese mathematics. Basically, he is saying that since 1868 or since the middle of the Edo period, which would be 1700 1750, Japan has been following Western knowledge, Western culture, Western technology. He said that the discipline of modern science originated in 17th century West. Before that, however, perspectives of nature as well as approaches to it differed considerably according to the place, nationality and time. This fact suggests, he does not say prove, but he just suggests that the modern scientific view of and approach to nature is neither unique nor absolutely correct, something that should have been obvious to us, except for the fact that while we learnt modern science, we learnt no other science of any other civilization, and therefore we thought that that is the only way of doing things. I mean, other than that there is no profound discovery here. It arises because of a very deep awareness of a different tradition of mathematics or a different tradition of science. So, suggests that the modern scientific view of and approach to nature is neither unique nor absolutely correct, and that there are alternatives as to the direction modern science should take or could take. And then he says we are studying history of India, China, Korea, and this put in his web page on. Okay, so with this sort of the technical aspects of proof and its philosophical implication for the development of mathematics in India, more or less we have had an overview. There are many issues which are unclear, and in what I have tried to present, maybe I have tried to show the picture somewhat in a very elongated way in somewhat in one direction, but analysis of many more texts which contain proofs in Indian mathematics and astronomy will be able to give us a more balanced overall view, but the view will not be that Indians were following Euclid or Indians were following Althussi or somebody. They were having their own methodology for doing mathematics, which was fairly sort of rigorous, accurate. It would have been restricted in its outcomes like any other approach to mathematics would have been, but it was creative all through. It was not that mathematics stopped with the Greeks and then had to sort of start on a different foot in the Renaissance times and get reformulated in the Greek way in 19th 20th century. The same idea of rigor more or less persisted in the way Indian mathematics moved, and I think with these comments I will stop this lecture. Thank you.